Welcome to the recording of the Developing a Site Characterization Plan presentation from the Back to Basics Part 1, Developing the CSM and Site Characterization Plan workshop that NMOA hosted in March 2018. So this session, Developing a Site Characterization Plan, is presented by Ryan Wymore from CDM Smith. He is an associate in the Denver, Colorado office, where he serves as a technical strategy leader focused on the evaluation, selection, pilot testing, design, and operation of soil and groundwater remediation technologies. He spent the last 18 years specializing in innovative remediation technologies, particularly in situ bioremediation, monitored natural attenuation, in situ thermal remediation, in situ chemical reduction, in situ biogeochemical transformation, and in situ chemical oxidation. He has managed projects, designed and executed pilot studies, and served as the lead engineer for design and implementation of full-scale remediation projects. He is a 16-year member of the Interstate Technology Regulatory Council, which is the ITRC. He has been a member on 8 technical teams and has served as an instructor for internet and classroom training seminars, particularly on DNAPL characterization and remediation technologies. He was on the ITRC Board of Advisors as an industry representative. Ryan holds a Bachelor of Science in Biological Systems Engineering from the University of Nebraska and a Master of Science in Civil Environmental Engineering from the University of Idaho. He is a registered professional engineer in Colorado. So with that, take it away, Ryan.
All right, thanks, Jennifer. So this session is developing a site characterization plan. So for this talk, based on earlier sessions, we have already developed the initial conceptual site model. So we've already gone through the process of trying to assemble what releases happened at a site, where the contamination is presently, what we know about fate and transport, all those kinds of things. However, in doing that initial CSM, we likely have identified data gaps that need to be filled. So at this point in the process, we're going to talk about how do you develop a site characterization plan to go out and collect data to fill those data gaps. When we're doing this and going through this process, we recommend an iterative approach. So in other words, it's unlikely that you'll be able to just conduct one characterization event or one sampling program that's going to answer all your questions and give you what might be considered the final CSM. You're probably going to have to go through more than one iteration of conducting activities, collecting data, filling those data gaps, and then updating the CSM, and then generating new data gaps that you need to address. This is all summarized in some recent ITRC guidance document that I'm going to refer to and use for portions of this session. That document is the ITRC Integrated Site Characterization Process, which came out in 2015. So in that document, the ITRC came up with this concept of objectives-based characterization. So we're not talking about remediation objectives or cleanup goals here. We're talking about objectives for site characterization. So we want to establish and enumerate objectives that say exactly what we're trying to do with our specific site characterization program. So this is a systematic, stepwise process that can look a lot like the old triad approach, which we've shown here on the bottom of the slide, where you have a planning phase, you have dynamic work strategies, and you use real-time measurement technologies to the extent that you can. So as with many ITRC documents, we came up with a flow chart because this process really does lend itself well to a flow chart. This is divided into 3 kind of modules. One is planning, tool selection, and then implementation. So the planning module is what we're going to go through first. And this is things like defining the problem, identifying the data gaps, developing these data collection objectives that I referred to a minute ago, designing the data collection and sampling plan. And we want to point out that this is similar to the EPA data quality objectives process. So here's the flow chart. Over here on the right, the planning module is shown here. So we'll go through these 4 steps. The tool selection is in the middle, and then the actual implementation of the investigation and collecting the data is down here at the bottom. All right, so one thing that we want to point out is that this is very similar to the DQO process, and they're kind of built in. So we didn't want to create some steps in a flowchart that were certainly not going to replace the EPA DQO process, but really it's just kind of a way of restating them. So if you follow the DQO process, you're going to inevitably be following the same process in our planning module that we are recommending here. So step 1, this is where you're defining the problem and assessing the existing CSM. So at this point in the process, there has been the initial CSM developed. It might be fairly rudimentary, or it might be pretty well developed depending on how much data were available to build it. But still at this point, you're defining the uncertainties. So what do we not know still about the site? So to kind of illustrate some of these points and to drive the concepts home, and this is also part of the ITRC training, we have a simple case study that was a real site from some of the members of the ITRC characterization team. And we include it at various points in these slides just to illustrate the steps in the integrated site characterization process. So this is a Drycleaner site with shallow groundwater. You can see the map at the right where the black dashes outline the initial take on where the plume is. So that's the extent above standards. You can see it's right below a Drycleaner. You can see some of the data collection points that were on here. So basically, without specifying what the actual concentrations and whatnot were, we just kind of showed a simple color code that if it's red, it's above the criteria, and if it's green, then it's below. So the triangles are monitoring wells, and the circles are soil borings. So this is what was considered the initial CSM here. So this is kind of our problem statement step. And if you look at how this was done for this site, they really didn't do too bad of a job, considering this was several years ago when this initial work was done. I think a good 10 to 15 years ago now. So they had done 18 soil borings at 5-foot intervals. So there was some attempt at vertically discrete soil sampling. The monitoring wells were not they weren't really out of line with what we do in some cases now. So there were 5 wells with 10-foot screens. So it's not like they were sampling wells with a 40 or a 50-foot screen. They were 10-foot screens. So this is what was used to generate this initial conceptual site model. Within this blue circle here, that was considered the source area. And there were in situ chemical oxidation, or ISCO injections, and bioremediation injections being done in and around the source area and the plume to try to lower some of these concentrations. So now looking at this and kind of converting the CSM to a problem statement, one thing is you notice that pretty much the entire outline of the plume is shown with a dashed line. So that's implying that there wasn't a lot of confidence in the definition of that delineation, especially in the down gradient direction. So down at the bottom right of the slide where we show groundwater flowing to the southeast, there was a lot of uncertainty as to where that plume ended, just because there's big areas where no measurements were collected. The second thing is the source area, the location of the source area, and really kind of the characteristics of it were inferred but not confirmed. You'll notice just a handful of soil borings and only one monitoring well kind of around that blue circle. There really wasn't any kind of a plan in place to monitor the remedy. And then also, one question you might be asking already, given that this is a shallow groundwater site, is what about soil gas or vapor intrusion? Well, that was completely left off of this first investigation, so that's obviously a huge data gap. So step 2 is identifying what the data needs are and what resolution we might want to think about. How high of high resolution tools do you need to use, for example? So this is just an example of 2 different ways to deploy samplers to try to get at the resolution issue. So on the left, we show some transects. In this case, I believe these are passive soil gas collectors. So they're basically just kind of mapping hotspots, in this case in soil vapor. On the right, you can see a much more detailed picture because the resolution was a lot higher. There were a lot more measurement points kind of in a grid configuration instead of just in a transect. So just a couple of different ways to get at what might be going on at this site in particular, but it illustrates the idea that obviously more resolution provides better data. So speaking of resolution, I'm going to walk through a series of graphics and we're going to talk through when we can actually tell what we're showing here. So this is a resolution of 1 by 1, looks just like a square, 2 by 2. So we've increased the resolution by a factor of 4. 10 by 10, maybe you can kind of see what this is, and then you get to 20 by 20. And as we increase the resolution further, you can obviously tell that this is the letter R. So the question, and the reason I really like this exercise, is you have to ask which one of these is sufficient for the goals at my site. Obviously, the best one is the 100 by 100. That's the clearest, and you can, very easily tell what that is, and it's a nice sharp image. But that is a factor of 4 higher resolution than the one next to it. So what if the cost goes up by, that same factor? What if it's linear? So is it worth 4 times the cost to go from the 50 by 50 to 100 by 100? Well, maybe not. Maybe the 20 by 20 is good enough, depending on what you're trying to do. And so you have to try to find, the point is you try to find the best sort of mesh point of cost and the resolution. So we really like to include that in this part of the training because lots of people are out there doing high resolution characterization now, and those tools are fantastic and they provide great data. And I've got examples in here later on about, in addition to this Drycleaner case study, about how they can be used. But one of the reasons that sometimes people are hesitant in using them is because they do kind of fear that cost. Like, do I really need a measurement, every inch or something like that? And they kind of steer away from these tools because they perceive that it's just going to generate this, infinite amount of data that, costs a whole bunch of money and no one really knows what to do with. So that's why you have to match the resolution that you need to your site. So taking it back to our Drycleaner case study, this is how those data needs were translated into what we were going to try to do at this site. So we needed additional soil samples to really try to outline the source. The big data gap, at least when I first came on, looking at this site, was the soil gas and for vapor intrusion, and that's going to be done all over the place. And then lastly, additional groundwater samples needed to define the extent of the plume. So one other data gap is kind of the distribution of contaminants within this source area. So here we're showing a cross section and really kind of depicting the vertical dimension. So what does this look like with depth kind of across the whole site? So that was something that was unknown because they didn't really investigate that the first time. So I'm going to pause here for a second in our integrated site characterization process and talk about this idea called significant data gaps. So this is something that actually came from the ITRC Fractured Rock Guidance, which came out at the end of 2017. And we included kind of a very similar site characterization process in that document and actually referred to the 2015 integrated site characterization document. But one thing we included in the fractured rock document that I want to point out here is that this idea of significant data gaps. So especially at fractured rock sites, there are always going to be things about your site that you don't know, that you wish you had more information on, whether it's vertical distribution of contaminants or understanding of fractures or whatnot. You're always going to wish that you knew more. So what we're trying to do is avoid getting stuck in this endless loop of characterization. Like, oh, well, we found another data gap. We collected samples every 2 feet last time, but what if we need to collect samples every foot this time? That kind of thing. So this idea of a significant data gap actually came from one of our state members, one of his guidance documents that is used in his state. And the definition is shown on the upper left here. It's missing information that limits the formulation of a scientifically defensible interpretation of the data. So basically, some examples of when a significant data gap exists are when you can't conclude whether a release has occurred, or if you have potentially multiple release points, if you can't tell, which facility or which area is the source of a plume. Basically, if more than one interpretation of the data can be supported by what you've got. So in the realm of modeling, think non-unique solutions. So again, we want to point out that at fractured rock sites, you're almost always going to have some kind of a data gap. The question is whether it's a significant data gap that unless you address, you really can't move through the remedial process. So that's the main question to ask. So we listed some examples here. Like I mentioned, the lateral and vertical extent of contamination, where it's moving, receptors, how fast contamination is moving toward those receptors, etc. So back to our flow chart, we're on this third step of establishing data collection objectives. So again, these are objectives that are going to be used to govern the data collection process. So here's some examples of that. So over on the right, a characterization objective, like an overall objective for a site, might be to determine the lateral and vertical extent of VOCs. So obviously the data gap that came from is you don't know the three-dimensional distribution of contaminants. So a specific data collection objectives, rather than just saying, well, we're going to go determine the lateral and vertical extent of contamination, that's kind of vague. We want to get to a specific data collection objective that says something like, we want to collect data about the fracture orientation, the fracture location, the fracture connectivity, and the vertical and lateral concentrations of VOC at the source and down gradient toward receptors. So obviously we're assuming a fractured rock site here, but the idea is you get specific. So this data collection objective, then that allows you to pick what sampling methods you're going to use, how many samples you're going to collect, and so on. So another take on step 3, if we think maybe towards our dry cleaner example, you can say our objective is to delineate the extent of the dissolved phase plume to determine the plume stability and maybe get a handle on the attenuation rate. So to do that, we're going to collect groundwater samples at specified depths. We're going to collect soil borings every certain interval of feet. We're going to delineate the plume, so we're going to start, maybe inward and work toward the boundaries of the site until we get to standards. We're going to install wells, because remember, another data gap at this site was there really wasn't a performance monitoring program for the remedy. So kind of condensing all of that into specific objectives. Again, defining the plume extent exceeding standards, assessing the remedy progress with soil and groundwater samples, assess the vapor intrusion threat, and to do all this quickly. So they didn't want to be out in the field for, weeks and weeks at a time. So in terms of the resolution, the soil samples were going to be done with continuous cores. And then rather than predetermining what interval that was going to be sampled at. Remember, before they had done soil samples at this Drycleaner site at 1 every 5 feet. So rather than predetermining that, they left it to the field team to say, all right, whenever you see changes in lithology, we want to get a soil sample for VOCs and see what it looks like. For groundwater, remember that had been done with 10-foot, with wells that were completed with 10-foot screens. So during the grab sampling, we wanted to get samples every 4 feet. And then soil gas, the idea was to get 2 different intervals to try to evaluate, nearer to ground surface and a little bit deeper. So step 4, this is where, you've kind of already built most of the elements of your characterization plan. This is the step where you just document everything. So we're at this step in the process on the flow chart. This is where you're just putting pen to paper and essentially writing everything down. So you want to recognize the limitations of what you're doing. You want to address how you're going to handle the data that you're generating, because especially if you're using some of these high resolution tools, that might generate data that you're not used to dealing with. You may get something other than just a concentration of, micrograms per liter. You could get, some different types of data that you just need to handle differently. But then speaking of that, you do want to use real-time analysis. We really recommend that to the extent that you can, just because those tools can provide, so much, the data they generate can be so valuable. In terms of the types of data, this is a categorization we came up with for the ITRC document, and it's relevant for the next phase in the process, which is tool selection, which I'll get to here in a minute. But we talk about quantitative data. So this is when you're getting, a mass per volume, micrograms per liter, parts per million, etc. So it's compound specific values. So it's not, a vague measurement. We're talking, you're getting TCE concentrations of micrograms per liter. That's a quantitative data type. Semi-quantitative is something that provides, again, compound-specific quantitative measurements, but it's not in concentration. So a good example of this are the passive soil gas collectors, where you may get a measurement of, nanograms or micrograms of vinyl chloride or something like that. So it's compound-specific and it's quantitative, but it's not a concentration. And then qualitative is an indirect measurement. So in this case, think of like the profiling tools like LIF or MIP, where you have or a PID, where you're getting a measurement that provides a relative absence or presence, but it doesn't directly relate to a concentration. So like on a membrane interface probe, for example, you may get some responses in millivolts that vary with depth. So obviously that is, the millivolts is quantified, but you don't know precisely what that converts to in terms of a concentration. So we call those qualitative data types. So when we're designing our process, we want to consider accuracy and precision. So how close does the result come to a true value? That's accuracy, so that's on the left. Precision is reproducibility, but of course on the middle figure, you can be precise but not very accurate. Ultimately, we want to be accurate and precise. However, kind of a caveat to that is we're really pushing the use of these, field tools and real-time measurement technologies. But when you're doing that, you have to realize that when you're doing a hydraulic profile or a membrane interface probe profile, you're not getting data that's of high quality and is the highest accuracy and precision. It might be considered screening level data, but you're generating so much of that data for a relatively small expense compared to drilling a lot of wells and collecting samples, of groundwater and then having those results validated, to the highest degree. That can get really expensive. So we're, especially at this phase of the process, when you're still building your conceptual site model, these screening level tools that provide the real-time data can be very valuable. So when you're documenting your investigation plan, when you're developing that plan, again, we want to emphasize to be dynamic, flexible, and adaptable. If you're going to generate enough data, a field laboratory or some type of a field analysis capability can be really valuable. And then again, the idea of using real-time data collection so that you can update the CSM, really within days as you're generating data in the field. Another thing to include in the work plan at this phase is you have to define the parameters within which the field team can make decisions. So, for example, if you lay out a grid of sampling locations, let's say it's groundwater grab samples, and you define a grid of 20 locations, it's probably not a big deal if the field team has to move one of those locations by a couple of feet to avoid a utility. However, if there's some kind of a subsurface condition that you find when you start getting into the field, that maybe 15 out of your 20 planned collection points you can't do because there's some obstruction or some utility or something, then that's probably something where you should convene the project team and really try to decide what you need to do. So that kind of decision-making process, you can define that in your work plan and say, okay, how much can the field team leader or the lead geologist or whoever is leading the program, what can they change kind of on their own? And at what point do we have to stop work and re-engage everyone and then decide what to do? So at the dry cleaning example, the tools that they wrote into their plan were some soil vapor sampling, a field lab that could do both soil and groundwater, and also some soil vapor samples. So what that looked like in terms of the site plan is shown here. So we're showing kind of some of the old data points with some of the proposed new locations. So the proposed locations are shown in yellow, and the idea was those were going to be, relatively co-located soil and groundwater samples. So if you remember, we were trying to get soil samples at changes of lithology. When they got out into the field and they did a couple of these, they realized that that would be roughly about 5 soil samples per boring through the treatment area. And then for groundwater, if you remember, it was going to be a sample every 4 feet. So that turned into about 3 vertically discrete samples per boring. So you can see kind of the initial layout of where some of these were going to go. And then the last thing was the soil vapor. Again, that was one of the big data gaps from the initial investigation, was they didn't have any of these samples. So you can see the layout of proposed soil gas points. The idea was to collect 2 samples per depth, and those are shown at the yellow circles where the initial plans were to collect those right there. So at this point in the process, one thing that was developed by the ITRC team that is really useful is what we call a tools matrix, or a tools table. So this is a downloadable resource that you can get from the ITRC, the Integrated Site Characterization team's website. We've got the link down here at the bottom of the page. And you can just open this up, and it opens in Excel on your own computer. So I've got some screenshots here to show you what this looks like. So it has well over 100 tools in it, and they are present in rows in the table. They are sorted by characterization objective. So whether you're looking at wanting to know something about geology, hydrogeology, or chemistry, the type of media, so unconsolidated or bedrock, saturated or unsaturated zone, and then the data quality that I talked about before. So you can actually open this thing up and not do any of the sorting or searching, and it just shows everything about all the tools. But that's really kind of overwhelming. So I really do suggest that you use some of these sortings to kind of break it down a little bit. So the way that you do that, first, any part of the tools table is clickable. So our team apparently came up with the definition of geology. So if you click on geology, this is what comes up, and it just describes what we mean by geology in this context. But the cool thing is you can click on any tool, and those are all hyperlinked to additional information. So here, for example, we have ground penetrating radar. We bring up literature references. So we tried to, as a team, include some of the important papers in the development of this tool and kind of some of their initial applications and what was maybe important to know about it. But if you don't want to go read a bunch of literature, we tried to put a short description of what the tool is, the type of data that you get from it, the data quality, and the advantages of the tool, but also the limitations and the disadvantages, because that can be just as important to know. So once you come up with a set of searches and you click the search button, then you get a result that might look like this. And the green boxes means that that tool collects that kind of information. So here's an example. Let's say, and the idea is if you're following this process kind of to the letter, you're going to have defined your data gaps, your data collection objectives, and started to write your work plan. And so at this point, you're saying, okay, I know what I want to do. Now I want to decide how I'm going to do it. What specific tools and technologies am I going to use? So that's when you can consult this tools matrix. So that was the idea. So again, it's a systematic process to kind of down select what you want to get to. And then you get to your results. So let's just run through some screenshots of one of the example searches. So let's say you pick geology, and then you go to this box and you pick lithology because we want some information on lithology. Let's click unconsolidated, saturated, and then quantitative in this case. So then you make all those selections and then you hit the search button, and then you get something that looks like this. So you get a list of, a manageable number of tools, something like, maybe 15 to 18 tools, with, each one of these tools meeting some kind of the data quality or the objective that you picked. If that's too many, if you do a search and you still haven't narrowed it down enough, then you can do it again and do another search on the results that you've already set up. So again, the idea is that you select this tool or the tools that you're going to use, and then you basically finish up your work plan, and then go out in the field and collect the data. So this tools matrix, I do also want to say, there's actually two of them. One was developed for this ITRC integrated site characterization document. We created another version of that tools matrix for the fractured rock team and the fractured rock document that came out in 2017. The fractured rock one has everything in it that was in the 2015 version. It just has some additions. Ideally, we wanted to try to do them to just point to the same one, but because of some of the factors related to how the ITRC website works, we had to kind of duplicate it and then add to it. But the point is, they're both great resources. The one for the fractured rock document, it does have all of the tools that work in unconsolidated media in it. And the reason is because, a lot of fractured rock sites still have a component of overburden that you have to deal with. So we didn't want to just completely eliminate the overburden. But anyway, they're both great resources available from each of the specific teams' document webpage. So again, back to our case study. Now, they had done this work, obviously, before we finished developing the tools matrix, but let's just say, let's apply the tools matrix to the situation from this case study. So again, there's the objective, delineating lateral and vertical extent of the dissolved phase plume. Look at plume stability, and rate of attenuation. So we wanted to find the boundary that exceeds groundwater samples. We wanted to assess the remedy progress in the source, and then assess the soil vapor. So you would go into the tools matrix with this kind of a setup. So chemistry, contaminant concentration, unconsolidated, saturated, and quantitative. And then that would yield this set of results, which has a lot of things in it that are based on sample collection, which of course you would expect. This is just a zoomed in version of it, so you can see a lot of the vertically discrete groundwater sampling tools are on here. Some other stuff that still might apply, like molecular tools, mobile labs, and then some of this direct push logging. So you can see, you're certainly not going to use all of these, but then the idea would be that you would pick from them and then put that in your work plan. So this set of search conditions returned 21 tools. So then, the ones that the project team used, basically the point is that this tools matrix would have yielded basically what the project team did here. So they had direct push sampling for soil and groundwater, which we already talked about, the active soil gas surveys at 2 different intervals, and then the on-site lab. So again, just to summarize the tools matrix, you use it at a point in the process where you've already set some of your objectives on what you want to do. It's just interactive, but it's also a standalone matrix. So you can, like I said, it's an Excel file that you download. You just have to enable, some of the macros and whatnot in Excel to get it to work. And then, you're off and running with it. All right, so now at this point in the process, we've covered the planning module, which is the first 4 steps, the tools selection, which is the Excel tables, and now we're to the part where it's actually time to get out to the field. So this is where we're implementing the investigation. So 6, 7, and 8, implement the investigation, do the data evaluation and interpretation, and then update the conceptual site model. So again, I want to emphasize on the characterization plan itself, because at this point you're getting ready to go out into the field, and this should all be done. So it's centered on these characterization and data collection objectives. You're talking about how you're going to collect the data. You're including the specific tools that you're going to use, and you're forward-looking to data management. How you're going to handle the data, and that's especially relevant for fractured rock sites, because you may be doing, some geophysical logging, maybe some televiewer logging, and you're generating the kinds of data that maybe you're not used to managing if your only experiences with unconsolidated sites. So some of that can require specialized tools to be able to handle, visualize all those kinds of data. So you don't want to wait until you already have the data to realize that you don't know how to handle it. You want to look at that at the work plan stage. Then you want to talk about how you're going to evaluate the data. So again, just one final point on, our emphasis, even at fractured rock sites, to try to use this dynamic approach, where you're deciding what to do next based on what you've already learned at a site. So this is, again, the real-time measurement technologies where you can collect data, over the course of a few days, and then be looking at some of those results as they come in to decide where to go next, because you might find that, you develop an initial plan to, investigate certain locations, but if you're willing to look at the data as you're generating it, you can end up saving a lot of time and money, because maybe there's areas that you were thinking you had to investigate that you don't. So again, as I mentioned before, the work plan should outline how those kind of decisions can be made, and who can make those decisions, and who needs to be involved in that. Now, another point is you want to establish in your work plan how often the project team is going to communicate. So I've kind of been speaking a little bit in the negative, like, okay, what if something goes wrong? Who do you call? You also want to plan for just kind of the normal course of operations. If you're using tools that generate data in real time, you might want to plan to have, a call with your project team and with your client, maybe a couple times a week, maybe every day if you're generating data pretty quickly, just to discuss what you're seeing. To say, all right, this is, we did logging at these 5 points. These are what the data are telling us. Our original plan was to go do points 6 through 10, but maybe we should actually go do points 11 through 15 based on what we saw. So defining the communication in the work plan is a good idea as well. So some last kind of additional words of wisdom that I put in here, and this is kind of stepping away from the ITRC process, but just some things that I think can be valuable during this, when you're developing the site characterization plan and you're going out to the field kind of early on in the process. So again, you've developed your initial conceptual site model, and you're doing some of the first, I guess, supplementing or building of the CSM, where you're collecting data to build on what you know about the site already, but maybe you're still a ways off from, actually having a decision document, for example, or a ROD. So one point, and this actually is, a message from some of the ITRC documents, is to understand the difference between characterization and monitoring. So characterization, that's when you're trying to understand what is happening and what has happened at your site. Monitoring is just what it says. It's for monitoring, for example, a remedy. You have a remedy operating, pump and treat, ISCO, bio, thermal, whatever, and you're monitoring how that remedy is going. Maybe even it's M&A. So what this really means is ITRC really strongly advocates to not use monitoring wells for some of this initial site characterization. Just because there are so many great tools that are available, that I've talked about a lot of them already. Some of the profiling tools, some of the real-time measurement tools, those are appropriate for site characterization. We really want to get away from, now obviously this is at sites where you can do, direct push, for example. If you have a site where you can do direct push and you really don't know the extent of contamination, it's much more appropriate to do, groundwater grab samples, like a screening level sampling, and to do a lot of them, as opposed to just going out and drilling 20 wells and kind of guessing where you're going to put them and then sampling those wells. You can actually use the characterization activities to decide where you want the wells. And maybe instead of needing 20, you might only need, 10 or 5. So kind of along those lines, especially initially where you're really trying to build your CSM, value the quantity of data over quality. So this is, again, leading us towards the profiling tools, towards field labs, towards field measurements, because you want to get a high volume of data, even if it's not of the highest quality, because you're going to use this initial data to decide what to do next. So there will be a time for, collecting the higher quality data later on, when you're trying to assess the performance of a remedy, when you're trying to decide if a remedy is done. That's obviously a time, to collect higher quality data, and not use a DPT groundwater grab sample to decide if, you're inside or outside of the plume. So again, especially at early phases, get as much data as you can. And then a last word is to not wait to deploy some of the innovative tools and technologies that are out there. So some examples that I've got here are things like the molecular tools. So if you have, a site, maybe it's a petroleum site or a solvent site, there has been so much work done in advancing how we can characterize the microbial community. For just a few samples, you can really learn a lot about your site that can have, implications for how you would select and design a remedy later on, or even how you would assess M&A at a site. So don't think just because you're in an early phase of characterization that you can't do some of that stuff up front. And then other tools that can be useful that are becoming more common are things like in situ microcosms, and then doing, incorporating mass flux and mass discharge evaluations. All right, so I've got a few words on each one of those technologies. So again, for molecular tools, you don't have to wait until you're, at a design phase and you already have selected your remedy. These tools can be really instructive early on. They can tell you, could I expect much degradation at this site? Could M&A help me out? And you can learn that just by adding in a small number of samples to your investigation. So I've included one example here is this technique called QuantArray from Microbial Insights. There are others that are out there, but the idea is you can collect, essentially add a sample on to a few of the locations that you're already going to be investigating. And you can learn a lot about the microbial community. Again, whether there are bacteria there that, are known to degrade the contaminants that you have, whether they're completely absent, those kinds of things. And, these samples, on a per sample basis, they can get fairly expensive, but if you're only adding in 4 or 5 of these samples, it can really help you learn a lot about your site. So another thing that's becoming more common, and of course there's an ITRC document on it, is the use and measurement of mass flux and mass discharge. So this is a document that the ITRC DNAPL team put together. It came out 8 years ago now, and it's got to be one of the most popular and most used documents ITRC has ever done, just because it has some really good information in it. And this idea of using mass flux and mass discharge can also be a way to help you understand your site at an early stage of building the CSM. So I'm just going to talk quickly about what mass flux, mass discharge is, and then what's in this guidance document. So the traditional approach, obviously you're measuring concentrations, milligrams per liter, micrograms per liter, because that's what all our regulatory standards are based on. So let's say you have this scenario where you've got, a well that's a receptor down here, and you take a sample and you measure the concentration. The mass discharge approach, you actually draw or create a transect, so some kind of a cross-section. There's different ways to do it that I'll get to here in a little bit. But basically what you're trying to do is trying to quantify how much mass of the contaminant is moving past this plane. So you can think of it as kind of, installing a virtual window pane in the subsurface, and then you're actually adding up how much mass is coming across that plane. So instead of getting a milligrams per liter or micrograms per liter, you get a grams per day or a milligrams per day or a kilograms per year, that kind of thing. It can help you, it's just a different way to look at your site, and it can help you to understand whether you've got a whole bunch of mass moving through a site, or maybe it's just a small amount of mass and you just happen to have a well that's maybe in a bad location. So the key point is that this is sometimes a better way to understand what's going on at your site. So the guidance talks about, thoroughly treats this subject. So it talks about the details of the concept, what mass flux and mass discharge is, and then also how you can measure it. There's a whole segment on the training that's associated with this, as well as a big section in the document that talks about the measurement methods. Probably the most common one that people think of is what we call the transect method. So this is where you're physically, you're either installing multi-level wells, or you're collecting grab samples in a transect configuration. So in this case, at each one of these 4 locations, you're collecting vertically discrete samples, and you are measuring the concentration in those samples. But then you're also measuring the hydraulics, because the flux you get at by measuring both the concentration and the groundwater flow. So that's how you get to a mass per unit time. So anyway, the document talks about how you can build these measurement methods, which ones might be better for certain situations. It just describes how you can use all of them, provide some case studies. So a couple of things to point out, and the reason that I say not to wait to look at this for your site, if you have it kind of in mind, like, all right, I'm building my initial CSM, I know that at some point we want to use an assessment of mass discharge or mass flux. You have to be, kind of the opposite of the molecular tools. You have to be intentional about how to get these data. It's not the same as just like with the molecular tools of, adding one sample to 3 or 4 locations and you're going to learn something. You have to design your whole data collection program around getting the mass flux and mass discharge. The reason I say that is because you have to have, if you're using the transect method, for example, you obviously have to define where you're going to put the transects, and you have to get them oriented correctly, and you have to get the spacing right. If you're using one of the other methods, there's an active pumping method. That's another one. You want to know where you're going to be pumping from, because there's ways you can do it that would bias your results. If you're going to use an active pumping method and you put your well right in the source where you know that there's NAPL, that's going to impact your readings and give you the wrong mass flux, basically. So this can be a very good tool to use as you're building your CSM, but it's not something that you can do as an afterthought. I guess that's the point. You have to design your characterization program to be kind of centered on this if you're going to use mass flux or mass discharge. All right, so at the end here, I've got a couple of case study examples that I want to walk through that just talk through some of the principles that we've gone through. So this first one is the Commerce Street Plume Superfund site. This is actually one that Michael and I have worked on together. So I'm showing over here at the right, this is kind of the, I guess what we would consider the initial CSM, the initial conceptual site model when we started working on this project. The purple is TCE greater than 5 microgram per liter, so that's the drinking water boundary or the MCL boundary. Within that, we have this green line, which is greater than 500. So the way the remedy was constructed, it's a multi-component remedy. For the lower concentrations between the purple and the green is going to be treated by MNA, so less than 500, greater than 5. This red contour was defined as a hotspot of greater than 50,000 micrograms per liter, so 50 milligrams per liter. So everything between the green and the red, so greater than 500 but less than 50,000, was going to be treated by remediation. And then this really hot spot, this really high concentration area was going to be treated by ISCO, so greater than 50,000. So here, just for context, there already has been a ROD signed, so we're in the pre-design phase. So we're trying to do pre-design characterization and then do a pilot study of how this combined remedy might work. So we use this integrated site characterization process that I just went through. So we assessed the current CSM, and then we identified data gaps, and then we set objectives and selected tools to go out and fill those data gaps. So just to summarize what the initial CSM was, in terms of the release, it was a DNAPL, TCE DNAPL, released into this sandy aquifer that basically went to about 40 feet below ground. That sand was subdivided into 10-foot zones, which were designated shallow, intermediate, and deep. And then there was a clay layer that was found to be continuous throughout this whole area that isolated the solvents above it, and that's been confirmed all over the place. There's been many samples that have encountered that clay. So anyway, this was the initial CSM. So over here at the right, you can see kind of an initial concept of what the remedy may look like for this site, where these hatched rectangles are biobarriers. So that's, amendment being injected either into wells or direct push points or some configuration to try to intercept the plume. So that was the idea. And then there's a grid of injection points in the ISCO hotspot. So it was going to be a very intensive and aggressive injection program for the hotspot, and then a little less aggressive in terms of the biobarriers. So going through the characterization process, or the integrated site characterization process, we identified the tools that I show here on the left. So we use the MIHPT, which gives you both contaminant and hydraulic profiling data. Different parts of the site, we also use the Waterloo profiler, which is just another hydraulic profiler. And then we did depth discrete soil and groundwater sampling, and we generated enough data that it justified having an analytical capability on site. So we did have a field GC on site to help analyze our samples. So some of the key findings from this investigation program are that hotspot, the red line that I showed before, does not exist anymore. Since the time of the RIFS to now, that hotspot has attenuated. Now there's still higher concentrations out there, something like 15 to 20 or 25,000, but that's less than half of what had been defined before. So that was obviously a key finding of this investigation. Another interesting thing that we saw is in one part of the site, we had basically just seen TCE everywhere out here. There was very little degradation. But there's one kind of big area of the site in the east central part of the site that was all DCE now. And so over the years, it had just slowly degraded from TCE to DCE. And then one last finding, of course, the sand unit does not behave as 3 separate 10-foot zones. It's pretty much continuous, and it just has a lot of interfingering and interbedded silts and even some clays that show up in different parts of the site. So basically from ground surface to 40 feet, it's a lot of sands and silts, interbedded. It wasn't just the three sand zones and then a clay zone at the bottom. So some of the important findings, because that hotspot's not there anymore, we don't have to use ISCO. So that's basically, eliminating a whole remedy component. Now we realize we have to expand bio to treat, spatially to treat the area where ISCO was going to be used, but that represents a really big cost savings by not having to use ISCO out here. So that, far and away paid for, probably 10 times over, paid for the characterization program that we implemented just by virtue of the fact that we don't have to implement that remedy component. So we're using this new CSM to design our pilot testing phase that we're just getting ready to start now. And then ultimately the remedial design is going to incorporate this new CSM. So another case study example is the Bountiful site. This is another EPA Superfund site. And here it's a little bit of a different scenario, although the part of it where, we did not develop the initial CSM, just like Commerce Street. We didn't develop the initial CSM here. We were given the initial CSM. And then we had to kind of decide what to do with it from there. So at this site, this is another pretty shallow site. And this was the initial CSM. There was a sand and gravel zone, basically from about 25 feet to 40 feet, just to keep it simple. And then below that, there was thought to be a clay aquitard, much like Commerce Street, that just kept everything above it. So in terms of a cross section, so this RI was done, 15 years ago or so. So that's kind of the rudimentary figure here. But this is basically what the initial CSM was. This white is the sand zone that's contaminated. And then there's this big, thick clay layer, tens of feet thick that kept everything above it. So again, we came onto this project after the rod, the rod was being developed. The feasibility study had been done. And the remedy that was picked was bioremediation. So, kind of a lot like Commerce Street, the design here was to use a grid pattern in the source and then biobarriers. So the biobarriers are the thick black dashed lines here that were going to be installed to intercept the plumes. So we, again, undertook a pre-design or a pre-construction, characterization out here. This was about 10 years ago, so we didn't have the same availability of tools, but we did have membrane interface probes. So we did MIP all over the place out here in the source area, in the high concentration parts of the plume, and then we moved down gradient. So we combined the membrane interface probe with depth discrete soil and groundwater sampling. We also used part of the membrane interface probe is the electrical conductivity probe, the EC, and you can use that to detect where you have silts and clays at your site. So we had found that if we got a certain response out here at Bountiful in the EC log, then we knew it was a clay unit. So yeah, we actually had confirmed that with some DPT sampling. So where we had seen an EC response, we went right next to that with a DPT rig and, pushed down to that location and grabbed a sample just to double check the lithology to make sure that that response that we were seeing in the EC actually was a clay. And we did that in, 10 or 12 different places, and every time it correlated. So we were confident that, that was a correlation that we could trust. So anyway, the results of this, basically, as you might imagine or might infer, is that we had concentrations of VOCs at high levels much deeper than what the initial conceptual site model told us. So again, if you remember, we were supposed to be shallower than 40 feet with everything. We found concentrations up into the thousands. Down here I show 15,000 micrograms per liter, down at 55 to 60 feet. So it was a lot different than what the initial CSM told us it should be. And then that clay layer that was supposed to be present at 35 to 40 feet, it was really only present in a few locations. I guess the bad luck here was that the few places where the initial RI sampled for it, they actually found it, but we really didn't see it anywhere except for those locations. So we had to modify our approach. We used that VPT-EC approach that I mentioned earlier to find where the real clay unit was, and it turned out that was down to about 80 feet, and that one was continuous. It was many feet thick all over the place. But what that really changed for us is, instead of having a 15-foot thickness to treat, we had something like a 40 to 45-foot thickness to treat. So it doubled to tripled the volume of aquifer that we had to treat with the remedy. If we would not have done this characterization, the remedy would have completely failed, because we would have missed the highest concentrations that were present at this site. So we had to design the remedy. So when you're doing an injection-based remedy, you can't just automatically screen over the entire thickness you're trying to treat, because if you install wells with a 40-foot screen and you try to inject into them, you're going to get preferential distribution, where you're going to have big parts of that thickness that don't get treated. So we had to modify the remedy to have smaller nested injection wells, and then we put monitoring wells throughout and whatnot. But again, the whole point of this was we took the initial CSM, and we did identify some data gaps, and we realized we kind of needed to confirm what that was telling us. And it turned out that the site really was a lot different than what the initial CSM said. All right, so back to our Drycleaner case study. What did steps 6 through 8 look like? So here is step 7. This is evaluating the soil and groundwater data. So we're using the same kind of a scheme, where the red is above criteria and the green is below criteria. And again, the triangles are groundwater data and the circles are soil. Now, this is some example soil data. So this is actually co-located. You can kind of see the circle behind it there. But I just want to show an example of what some of the data look like from the site. So they were collecting soil samples every 2 feet in this case, using the mobile lab. So you can see there was quite a bit of variability. So if we think back to the old data from the site were generated with a 5-foot interval, right? So let's say you were going from 6 to 10 feet, or from 5 to 10 feet, sorry. You would have been somewhere in here. You would have been reflecting some concentrate, or some combination of non-detect, 3.3, and 11.5. So this shows you kind of the value of the higher resolution data. One other thing to point out, just because we like to show real data, and real data aren't always perfect, the fixed lab here really didn't match the corresponding field lab sample. So it was 3.25 compared to 21. So that was something that the project team had to deal with. Now, I think it turned out that this was one of the only areas where they had that kind of discrepancy. But that's something that can happen when you're using a field lab. You certainly want to include split samples, and sometimes you have things like this. But again, they determined that it wasn't like a systemic quality issue. It just was kind of a one-time thing there. All right, so in terms of what the new data look like, this was the new interpretation of the extent of groundwater contamination, shown in red. So you can see that the contamination did move further to the southeast. And the reason that's important is you can see these red boxes. There's lots of residences around here. What about this idea of why the remedy really wasn't reducing concentrations? That was another factor here, which I'll get to in a minute. The soil vapor, this was one of the biggest data gaps from the initial conceptual site model. So here there are 3 different levels. Green is the one that's below all levels of concern. Blue is above chronic, and then red is above subchronic. So red is the worst, blue is kind of middle. But the point is, you can see there's all kinds of reds and blues in the soil vapor. There's not very many greens. So they were right to be concerned about the soil vapor pathway. It turned out, because of changing conditions out here and where the water table was, the original plan was to get soil vapor samples from 5 and 10 feet. Apparently the water table had come up quite a bit, so they just got 2 samples, one from 3 to 4 and one from 4 to 5. You can see kind of some differences between the two, and then this was a comparison of a split sample. A little bit better agreement than for the soil. So the step 8, I mean, step 7 and step 8 are kind of similar. So step 7, you're evaluating the data that you're collecting at that time. Step 8, you're kind of folding it all together, and you're taking the new data and putting it in with the data that you already had to get a new updated CSM. So putting everything together here. So we're putting the soil vapor with the circles, and then the soil samples and the groundwater samples, the new stuff, all on this figure. So this is kind of integrating everything together. The black, that's the old TCE contour for being above the drinking water standard. This is what it looked like now. It was kind of the same in some areas, but as I described before, it went quite a bit further toward some of the residences than previously thought. Kind of the last piece to this was what did the source look like in kind of that third dimension? And moving from left to right across the site, this is just a general depiction of where there was residual source material. And basically what happened was they designed the remedy not really knowing where the vertical distribution of the source sort of ended. So they were operating a remedy not knowing the source was a lot bigger than they actually thought. So that was the reason why the remedy hadn't been, or the concentrations really weren't responding to the remedy, because there was a whole bunch more source area than what they thought. So again, this is the visual depiction of how you kind of tie everything together. This was the outcome. So just so everyone knows, that wasn't the only step that they did for soil vapor. This was basically the first step. It confirmed the need for additional investigation to look at residential and commercial indoor air evaluations, and it led to, I believe, some mitigation for some of the commercial buildings around there. Within this characterization program itself, by looking at the data as the data were generated and reviewing results daily, the team was able to optimize where they were collecting samples. So this idea, convening kind of at the end of the day, looking at what you've got, and then deciding where to go next, they actually shaved a whole week off of this characterization program. So they got done what they needed to get done in 10 days instead of 15 days. So it saved quite a bit of money just for this characterization effort. So again, it's kind of an example of how, on the surface, these kinds of real-time tools and characterization programs might appear to cost more, but many times, certainly every site that I've worked on that has used these, they pay for themselves by some ability to optimize the remedy or even avoid a remedy component altogether, like I mentioned for the case example. So to summarize here, when we're talking about developing a site characterization plan and going out and collecting data, we want those activities to be driven by specific characterization objectives. The plan should be dynamic and facilitate real-time decision-making. And then you should always update the conceptual site model. Anytime you're out at the site, even if it's doing something related to the remedy, you can still use information you get while you're building or installing your remedy to update your CSM. So that's all I have for this session. I'd like to turn it back over to Jennifer.
Excellent. Thank you so much, Ryan. That was a lot of great information that I hope everybody finds very useful. So with that, I think we'll sign off here. Thanks again, Ryan.